Hi everyone, my presentation's title is Wireless Secret Sharing Game Between Two Legitimate Users and an Eavesdropper. My name is Miao, I'm the presenter. There are two co-authors, Dr. Hongbo Zhang from Middle Tennessee State University. I'm also from Middle Tennessee State University. And the third author is Dr. Dingde Jiang. He's from University of Electronic Science and Technology in China. So I'll first talk about the motivations and related work, then I'll introduce the system model. I'll then talk about the optimal secret sharing as a zero-sum game, and finally conclusions and future work. So we're in the era of Internet of Things. I have a cartoon picture here. It's in French. So basically what he's saying is that we have a teenager here and he lives in a smart home. There are a lot of smart appliances, like the refrigerator is trying to say, I need to be defrost. And the clock is saying, you have to go to your appointment zone. Then the washer is saying, you need to dry the clothes. And the faucet is saying, well, I'm leaking water, you need to have a plumber fix the problem as soon as possible. So we're really in a era of Internet of Things. There are a lot of things are connected nowadays. So I guess the progress is slower than I anticipated, but still we're seeing a lot of smart devices surrounding us. So the era of IoT brings both opportunities and challenges. One, I would say the one biggest opportunity or convenience is that everything, well, most things are connected wirelessly. But the challenge here is that security and privacy are very hard to achieve in wireless networks due to the nature of wireless communications. It's simply because in wireless communications, the signal can be received by anyone within range. For example, here, there's a wireless access point. It's sending signals to some computers, some legitimate users, but at the same time, say there's a wireless eavesdropper here. If this person is really close, then it can receive all the signals. So presumably, this guy here can figure out what's really going on among those legitimate devices. So it's very hard to guarantee security and privacy until there's some mechanism in place. Normally, a private key needs to be shared between wireless devices beforehand. The public key cryptography doesn't work very well because it requires a lot of computational resources. So it's not suitable for wireless or battery-powered devices. So often people use the private key to establish secure communications. So that's why usually when we try to connect, say, a computer from a wireless router at home, we have to configure the security key and mode on the router first, then we have to type in the same key on the computer. So it works, but imagine we are in the era of IoT. We have a lot of IoT devices, and some devices do not even have human interfaces. Like you have maybe an embedded device, there's no keyboard and mouse attached to it. There's no monitor maybe. So those devices must work independently without human intervention. So this is another challenge in IoT. Sometimes it's really hard to type in the private key or the passphrase to the IoT device. So this picture illustrates what problem we're trying to solve in this paper, or what kind of problem we're trying to address in this paper. So imagine we have two legitimate users, Alice and Bob. And not necessarily, I mean, we're trying to use two humans, but in reality, they could be two devices without any human interface. So let's say Alice and Bob, they're trying to exchange information using this communication channel, while this Eve is an eavesdropper trying to figure out what's really going on between Alice and Bob. So the question is, how can Alice and Bob pass the security key to each other when Eve is listening nearby? So essentially, how can Alice and Bob exchange the secret key without really a human, without some supervisor, step in and provide the key to both of them? How can they exchange the secret key automatically without any human intervention? So that's really the problem we're trying to address here. So in a nutshell, there are three different methods to do this secret sharing. First method is to exploit the randomness of wireless channels in the physical layer. So there are some representative works in this direction. The second method is to utilize the principle of reciprocity in RF propagation. So there are some works in this area as well. And the third method is to utilize the consequences of randomness of wireless channels in the data link layer. And there are some papers in this direction as well. And this is published by us in 2019. So I'm gonna focus on this method number 3 later on. So this is relatively new, this method number 3. And let me first try to explain how it works. So essentially, Alice and Bob, the two legitimate users, they try to exchange N packets in plain text, meaning that there's no cryptography involved. They just send information in plain text to each other. And we set the number of retries to 1, and there are N packets in total. The secret is simply generated from those packets. So you can simply do exclusive war. Let's say you have received the N packets. Then you simply do an exclusive war among those N packets. Then you can get another, say each packet is 64-bit or 128-bit. After you have done this exclusive war, among those N packets, you get another 64-bit or 128-bit chunk of information, and you can use that as the secret key. So this is the illustration of the process. So this is in the 802.11 environment. So in the beginning, Alice sends information to Bob, or Alice sends, say, half of the packets to Bob. So Alice first sent this add BA request, then the add BA response goes back to Alice from Bob, then it sends the acknowledgement, then the transmission phase starts, then there's a block ACK. So this will acknowledge all these packets sent by Alice. Then there's a tear down phase. Then the similar process happens, but now the Bob is the sender and sends packets to Alice. So how does it work? This seems to be very simple, and how can we really make sure that Eve doesn't get this secret or the exclusive war results of those N packets? So let me go back to this slide actually. So the reason it works is because in wireless communications, it's really hard to guarantee that there's no packet loss at all. So sooner or later, you're gonna have a packet drop due to noises or interference, maybe channel fading, etc. So those N packets, they can be sent between Alice and Bob. So Alice and Bob will receive all N packets. Sometimes if a packet's dropped, Alice and Bob may have to send one more. So totally their N packet received, say at Bob from Alice. So that's why those two legitimate users, they can have access to all these N packets, but the eavesdropper, there's really no retry for Eve. So if Eve misses only one packet, then she won't be able to get the exclusive war result. That's why if this N is fairly large, then sooner or later Eve is gonna lose one packet, and she won't be able to figure out what the secret is. So to make this work, so the idea is very simple. We just need to use the the wireless, the unreliable nature of wireless communications in a data link layer to make sure that the secret is only known by Alice and Bob, but not by Eve. But it works only when the probability of Eve receiving all these M packets is fairly low. So this picture shows the probability of Eve receiving 10,000 packets sent between Alice and Bob. So you can see the probability is so this is logarithm, and this is the probability. So here we're assuming that let's see here. So if the I guess this P sub E is the packet error of a single packet. So if the packet error of so if the error of the probability of losing one packet is P sub E at Eve, if this probability is very, very low, then Eve has a very high probability of getting all 10,000 packets. So this is like 1 out of 10 million. So if Eve loses one packet out of 10 million, then it can pretty much receive all the 10,000 packets. So probability is close to 1. And this probability goes down when the probability of Eve losing a packet increases. So towards the right-hand side, the communication is more reliable. So Eve has less probability to lose a packet. But the problem here you can see is that it does not work well when this P sub E, this is the single packet error probability at Eve. If this P sub E is not low enough, then this probability is pretty high. So in this area, in this red rectangle area, you can see Eve basically has more than half chance of receiving all the 10,000 packets. So this doesn't work well because the probability is too high. Eve can have a pretty good chance to figure out what the secret key is. So in this previous work, we studied how to minimize this probability by assuming that Eve's location is random. So assuming Eve is randomly moving between Alice and Bob or surrounding Alice and Bob, we try to figure out the strategy of Alice and Bob so that this probability here is minimized. So that's the previous work. This work was published in the journal paper. I think it's also referenced in this conference paper. So now let's talk about a system model and see what kind of new problem we're trying to address in this paper. So in this paper, we let Eve make her own decisions as well, and we use game theory to perform analysis. So the difference here is that not only Alice and Bob can make choices, the eavesdropper can also make her own decisions. So previously we assumed Eve's location is random, so Eve just has no clue about what Alice and Bob are doing. But now Eve is smarter; she can make her own decisions as well. So that's where the games, where the game theory comes into play. So assuming Alice and Bob's strategies is represented by this S sub L. So L stands for legitimate users. So there are 3 strategies between Alice and Bob. So S sub A means Alice sends all the M packets to Bob. And S sub B means Bob sends all the M packets to Alice. And S sub AB is the strategy of each one of them sends exactly half packets to each other. And similarly, we have Eve's strategies. We use S sub E to represent Eve's strategies. So Eve can pick 3 different locations. This L sub A is to stay close to Alice. L sub B stay close to Bob. And L sub M stay in the exact middle between Alice and Bob. So assume that Alice and Bob are d meters away. Also use L sub A, L sub B, and L sub M to denote locations of Eve. So this strategy of Eve is basically illustrated in this figure here. So this is the location close to Alice. So this location is epsilon meter away from Alice. And right here is the location close to Bob. and it's also epsilon meter away from Bob. And this L sub m is the middle point. So it's exactly d over 2 from Bob and from Alice. So Eve can freely pick either L sub A, L sub M, or L sub B. All right, so we have some notations here. We let P sub A of D, P sub B of D be the probability of Eve successfully receiving a packet from Alice and Bob, respectively. And D is the transmission distance. We have some assumptions about these two functions. The first one, each packet transmission is independent from each other. This means if I lose a packet now, it doesn't really affect, doesn't really mean that I'll have to lose a packet next time when I send. So each packet transmission is independent from each other. There's no correlation. And this P sub A and P sub D of D, they're time invariant. This is valid in slow fading channels. So let's say the channel is fading very slowly. This probability does not change dramatically over time. So it's pretty much constant in a short amount of time, during which Alice and Bob transmit those M packets. The third assumption, we have some mathematical expressions here. So this basically means it basically means the distance is the dominant factor in determining this error probability or success probability of receiving a packet from Alice and Bob. So if this eavesdropper Eve is closer to, say, Alice, so this epsilon is going to be a value between 0 and d over 2. So if distance is smaller, then it has higher probability of receiving the packet. And this is the exact half distance. And this is the further away distance, d minus epsilon. So closer Eve to Alice, then higher the chance that Eve will receive the packet from Alice. And this is the similar thing between Eve and Bob. So often the wireless channel is affected by channel fading, shadowing, noises, etc. But here we're assuming that the distance is motivating, or it's the dominating factor. So for a really long distance, then obviously you have lower probability of receiving a packet successfully. If you have a really small distance, then you have a higher probability. So we understand there are different factors, but here we're just assuming that distance is the dominant factor. So we're basically saying 5 meter versus 100 meter. So let's say for Wi-Fi, 100 meter, you pretty much couldn't receive anything, but at 5 meter, you can receive pretty well. So this last assumption is pretty technical, but this last assumption is based on the fact that wireless signal attenuation is proportional to distance squared. So that's basically what this last assumption is. So this is the this is based on the fact that in free space, the wireless signal attenuates proportional to distance squared. So now let's talk about this optimal secret sharing as a zero-sum game. We have some definitions. First, this strategy profile S sub L and S sub E star is a Nash equilibrium. If this utility function, so this is for the legitimate user that is a Bob, U sub L. So this is a utility function for that as a Bob, and this is the utility function for oh, I'm sorry. So those two utility functions, they're both for Alice and Bob. So L once again stands for legitimate users. So this is the definition for the legitimate user. So U sub L, S sub L star, S sub E star is greater or equals to U sub L of SL and S sub E star. So what it means is that this S sub L star ensures that for whatever other strategy Alice and Bob can pick, the utility function is always the best when this S sub L star is chosen. and we have the similar definition for Eve. So now we fix this S of L star. But now if this S of E star is chosen, then the utility function for Eve is going to be the greatest among all the strategies that Eve can pick. We haven't defined the utility functions yet, but this is just a very generic definition for this specific problem. So the utility function is the probability of Eve receiving all the packets sent between Alice and Bob. So we pick the positive sign for Eve and the negative sign for Alice and Bob. The reason is because Eve wants to maximize this probability, so that's why the sign is positive. And Alice and Bob, their goal is to minimize this probability, so that's why their utility function has a minus sign. We assume so we have two scenarios: the symmetric game and the asymmetric game. So let's first talk about symmetric game. So this is the definition of symmetric game. So this basically means the communication channel between Alice and Eve, and also the communication channel between Bob and Eve are identical. So if the distance is the same, then the packet sent from Alice to Eve and the packet sent from Bob to Eve has the same probability of received by Eve. We have this table 1. It's the utility matrix of the symmetric game. So Alice and Bob, this is the Eve, the 3 strategies for each parties. We have the utility functions in this matrix. Once again, plus sign is the utility function for Eve, and minus sign represents the utility function for Alice and Bob. We have this first lemma 1. This first lemma is an auxiliary result that will be used by lemma 2. This lemma 2 says this strategy profile SAB L sub m is a pure strategy Nash equilibrium. What it says is that if the communication channel is identical, then this strategy, meaning that Alice and Bob each sent half of the packets, and also Eve stays in the middle, it's a pure strategy Nash equilibrium. So this is basically what those 2 parties should select in order to maximize both parties' utility functions. So now this is the pure strategy Nash equilibrium. We now turn our attention to a mixed strategy Nash equilibrium. So what it means is that the strategy is no longer deterministic. Instead, is probabilistic. So Eve has some probabilities P1, P2, and P3 to use those 3 strategies. And similarly, Alice and Bob also have 3 probabilities to use those 3 strategies. So this lemma 3 basically says for symmetric game in a mixed strategy Nash equilibrium, Eve's strategy is to stay at the middle with probability 1. Alice and Bob should have positive probabilities on all 3 strategies, so that these 2 inequalities are satisfied. I don't have time to talk about the proof, but the proof is in the paper. So now let's focus on the asymmetric game scenario. So now assuming that P sub AD is greater than P sub B of D, this means when the transmission distance is the same, Eve always has higher probability to successfully receive a packet from Alice than from Bob. So this could be due to the fact that Alice may be having better transmission power. Maybe the communication channel between Alice and Eve is better. So there are all kinds of potential reasons for this to happen. So this is the utility matrix for this asymmetric game scenario. And this lemma 4 basically says, I'm not going to go through what these 2 inequalities mean, but I'm going to talk about the intuition. So what this really means is that if the communication channel between Bob and Eve is so bad, those 2 inequalities explain how bad it is. But the intuition is that if the communication channel between Bob and Eve is so bad, so much worse than that between Alice and Eve, then the best strategies of the legitimate users and Eve are basically to let Bob send the packets all the time, and also let Eve stay close to Bob. So what it means really is that things let's see here. So if Bob sends the packet, because it's hard for Eve to receive it. So that's why the legitimate user's best strategy is to let Bob handle it. So Bob will send all the packets to Alice, because this will minimize the probability of Eve receiving the packets. So that's why the legitimate users will let Bob send all the packets. And at the same time, Eve has to stay close to Bob, because it's really hard to receive packets from Bob. So Eve has to be really close to Bob. So Eve will stay close to Bob all the time. So that's the intuition behind this lemma 4. Once again, this happens when the packet success rate between Bob and Eve is much worse than the success rate between Alice and Eve. So lemma 5 says if the communication channel between Bob and Eve is not that bad. So this is like the contrary to this lemma 4 scenario. Then there's no pure strategy, Nash equilibrium. But in this case, at least one mixed strategy Nash equilibrium exists. And we have developed ways to find this mixed strategy Nash equilibrium for this lemma 5 scenario. So I don't think I have time to go through all the details, but those are the 6 equations that we have to rely on to figure out the this mixed strategy Nash equilibrium for this more generic scenario. Since this lemma 4 scenario probably doesn't happen very often, but this is probably going to be happening more often. So some definitions about what those equations are. And those are the procedures that we'll need to find this mixed strategy equilibrium. So essentially, it involves 2 steps: proposition and verification. So I don't have time to go through the details, but all the details are in the paper. There's a numerical example. We let n equals to 2. There are simply only 2 packets. We have the packet receive probability between Alice and Eve and Bob and Eve listed here. Then we find a mixed strategy Nash equilibrium. We first find out those 6 equations, and we use the procedure specified in the algorithm you saw earlier to find the probabilities, and this is the final result. So those are the probabilities for Eve, and the lower line is the probabilities for Alice and Bob. So that's pretty much the work. Then conclusions. We use game theory to model a secret sharing mechanism that exploits the consequences of the randomness of the wireless channels in the data link layer to share secrets. We have 2 different scenarios: symmetric game and asymmetric game. For the first case, we have this pure strategy of Nash equilibrium. For the asymmetric game case, a pure strategy of Nash equilibrium may exist under some conditions. When it does not exist, we should how to find a mixed strategy Nash equilibrium. Future work involves answering this question: do the results still hold when more strategies are available? The answer is yes. In a journal paper, we have extended the result to make it also work for the case when we have more strategies. And also secret sharing among 3 or more users, and more than 1 eavesdropper is another future work. And finally, experimentation over real and simulated wireless channels is another future work. Thank you.